Okay, so now you must have a question. What's the point of introducing totally unimodular matrices, right? The fact is total unimodularity gives us integer solutions. Now let's see the proposition. Suppose I give you a standard form linear program, minimizing C transpose X subject to AX equals B, AX greater than or equal to 0. For this standard form problem, if A is totally unimodular and B are all integers, then an optimal basic feasible solution reported by the simplex method must satisfy the integer property. Okay? As long as A is totally unimodular and B are all integers, then an optimal basic feasible solution must be an integer solution. Let's see why. For each basic feasible solution, there must be a basis B so that x can be decomposed into xb xn, where xn is 0 and xb is just AB inverse B. What we really need to worry about is whether AB inverse B are integers. To show this, there are several ways, but what we really worry about is AB inverse. Okay, so we know there is a formula for AB inverse. AB inverse will be just equal to this. Okay, the denominator is determinant AB. Certainly that's something we can do, and this ratio will be multiplied to this new matrix, which is the adjugate matrix. What's that? Just a review of linear algebra. A matrix is adjugate matrix is the following. The adjugate matrix, the element ij, is the determinant of the submatrix obtained by removing row j and column I from AB. Okay? If I give you a matrix like this, and I'm asking what's the ij element in the adjugate matrix, okay? Suppose ij are some given numbers. Then what you need to do is to eliminate row j and column I, and use the remaining submatrix to calculate the determinant, and then that will be an element in the adjugate matrix. That's just a linear algebra. Anyway, we don't really care about details because all we care about are these numbers. Determinant AB must be either 1 or minus 1. Okay? Because AB itself is a submatrix of A, and A is totally unimodular. So AB as a submatrix, its determinant must be either 1 or minus 1. For AB adjugate is the same thing, right? Because each element in this matrix is the determinant of a submatrix of A. Yeah. So the determinant must be either 0, 1, or minus 1. Yeah. So all the numbers here are 1 or minus 1. All the numbers here are integers, and the ratio must be either 1 or minus 1, so that after all the calculations, xb must be integers. Okay, that's how we prove that the optimal basic feasible solution must be an integer, as long as A is totally unimodular and B are integers. So, if you cannot understand fully the proof, somehow that's fine. Just try your best. But at least you need to memorize the conclusion. If a standard form linear program has a totally unimodular coefficient matrix, an optimal basic feasible solution reported by the simplex method will always be an integer. That's something. Or conversely, if I give you a standard form IP and the coefficient matrix is totally unimodular, then its LP relaxation always gives an integer solution. And that means solving that IP is equivalent to solving its LP relaxation. That means the branch and bound tree will have only one node, and that means the IP can be solved by running the simplex method once. Okay? And that means that IP is really not hard if the coefficient matrix is totally unimodular. So this provides us a very good example about the general way for doing OR studies or doing any kinds of research. The way to design a good method for solving a problem always starts from analyzing that problem. Once we know the coefficient matrix is so special, having this special property, then we may use a special method to solve it. In this case, the special method is just the branch and bound. It's not a special method, it's the original method, but the outcome will be somewhat special, right? We know for sure there will only be one branch and bound node, and the problem can be solved easily. So analyzing problems are really helpful if we want to solve them. Okay, so how about our MCNF problems? We need to make sure that our MCNF problem has totally unimodular coefficient matrix. One thing we will rely on is this sufficient condition for total unimodularity. Given a matrix A, suppose all its elements are 1, 0, or minus 1, and each column contains at most 2 non-zero elements, and those rows can be divided into 2 groups, so that for each column, we know for each column there are at most 2 non-zero elements, right? In each column, the 2 non-zero elements may or may not be in the same group, but they are in the same group if and only if they are different. So there are 3 conditions here. The first one certainly is required because if any number is not 1, 0, or minus 1, then that submatrix, the determinant cannot be 1, 0, or minus 1. And for the other 2, later we will see the example for our MCNF problem. You will see why we have this kind of somewhat weird condition. Anyway, as long as A satisfies all of them, then A is totally unimodular. If you are asking how may we prove it, there's a hint. We do it by induction on the dimension of square submatrices. We know for those 1 by 1 submatrices, they are all unimodular. Okay? And then we will make an induction hypothesis on the size. Suppose all the submatrices with dimension k by k are unimodular. How about k plus 1? That's something we will do. That's something we may do. I'm not going to really prove it in this course, and if you are interested, you may ask me if you want to know the detailed proofs. So now is the time to show that our MCNF problems, the coefficient matrix is really totally unimodular. Our problem is here, okay? For coefficient matrix of the standard form, because there are some inequality constraints, if we really want the standard form, we need to add some slack variables and to convert these inequalities into equalities, and the coefficient matrix will become larger, and it's not shown here. But let's assume the following. Suppose all the Uij are infinity. That means there is no inequality constraints. What will happen? Then the coefficient matrix will just be this one. Okay? Then we only have these numbers as our coefficient matrix. This coefficient matrix will fit our sufficient condition. Why? First, each column has exactly 1, 1 and 1 minus 1, so there are just 2 non-zero numbers. And also, all numbers are either 0 or 1 or minus 1, so the first 2 conditions are satisfied. Finally, we're going to divide rows into 2 groups, right? And what I'm going to do is the following. I'm going to divide rows like this. For supply nodes and the transshipment nodes, they are in the one group, and for demand nodes, they are in the other group. Then what's going to happen? For standard form, I need to change the right-hand side to be positive. Okay, so the coefficients will become plus, 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 minus, plus, and minus, so that the right-hand side can be positive. With that, immediately you can see for these two numbers, they are different and in the same group, different in the same group, different in the same group, identical in different groups, identical in different groups, identical, identical, identical. Oh, sorry, different in the same group, and then identical in the same groups. Okay, this is minus, minus. So this indeed satisfies the third condition we need, and it's not very unbelievable that any general MCNF problem satisfies this condition. Okay, so as long as we have this, it's very easy, just like this, to show that the MCNF problem has the coefficient matrix being totally unimodular, and therefore for MCNF problems, integer program can be solved by just running the simplex method once. Suppose, unfortunately, there are some positive Uij that is not infinity. Okay, then the previous argument is not enough because the coefficient matrix will be expanded. In that case, we need some more arguments. It's a slightly complicated and tedious process to show the cases with finite capacities. We're going to just ignore it. Okay, as long as you can get the concept, the idea here, then it's good enough. Now for this, it's just some more algebra, and let's skip it. Okay, so by combining all of them, we get proposition 3. For any MCNF problem that is feasible, the simplex method is going to report an integer solution. Okay, here we are assuming that this MCNF problem is formulated as a linear program. Then the simplex method solves it and reports an integer solution. If an MCNF problem is formulated as an integer program, then the simplex method solves the linear relaxation and reports an integer solution. Okay, so MCNF problems are useful because they can be solved easily. That's one thing. Later, we will show you another aspect. MCNF problems are useful because they can formulate a lot of different things. That's in the next video. Thank you.